Hello and welcome to Workshop 2. In this video, I'm going to present a few ideas associated with the Rutherford model of the atom. Not all the ideas that will be covered in the workshop, but a couple of key ideas. So the Rutherford model of the atom speaks to what we call the nuclear atom. But before I discuss this, let me just step back and talk historically about how the atom was conceived of or perceived before the Rutherford model. By the latter part of the 19th century, the electron had been discovered. The discovery of the electron is attributed to J.J. Thomson. So by the end of the 19th century, it was well established that there was a negative electron. It was also understood that stuff, matter, was comprised of positive material, which we now would identify with, for example, protons. So it was also natural to conjecture that, for example, an atom would comprise of some volume of space which was a uniform distribution of positive charge, and interspersed in this positive background would be negative electrons. This model was referred to as the Thomson or the plum pudding model. The background positive charge represents the pudding, and interspersed within the pudding are plums, which in this case are the electrons. So in this plum pudding model, where we have this positive charge and interspersed with a negative charge, this model is then can be subject to a test, and that's exactly what Rutherford set out to do. Because if the charge is uniformly distributed, a loose distribution of charge distributed uniformly in a volume of space, if, for example, you were to fire some positive charge particle at this, then what you would expect, since the background comprises positive with negative charges, you'd expect that there would be some deflection of that positive charge, but indeed the deflection would be through a small angle. So the conjecture would be that the incident charged particle would be deflected through some small angle theta. So let's test this. And the way Rutherford tested it was he used a positive charged projectile. In fact, he used the alpha particle. And the alpha particle is a helium nucleus. In other words, if you take a helium atom and you remove the two electrons, you're left with the nucleus of a helium atom, and that comprises two protons, which are positively charged, and two neutrons, which are neutral. Of course, at that stage, when Rutherford did this experiment, the neutron hadn't been discovered. But nonetheless, this is a positive charge. In fact, it has an atomic number of 2 because there are two protons. And the atomic number for helium is 2 because there are two protons. Now, Rutherford didn't use this language. What he was interested in is testing this plum pudding model of Thomson. And so, according to the model, is to reiterate, the particle, in this case the alpha particle, when fired on this target material, should be deflected through small angles. So the way Rutherford did this is he set up a source of alpha particles. In fact, radium decays by alpha emission. And he fired this beam of alpha particles. In fact, he made a beam by putting a collimator here. For example, a lead collimator. And he let this beam fall on a target material. And the target material that was used was gold, and we'll see why gold is a good target material. And then what he did is he simply measured the number of alpha particles that were detected at some angle theta. So we have this thin foil of gold. We have this incident beam of alpha particles. And we have a detector. And the alpha particles, according to the Thomson model of the atom, should be deflected through small angles. So what he did is he measured the deflection. In fact, what he did is he got his students to measure the deflection. They didn't have alpha particle detectors, so they put in little material like that scintillated, something like zinc sulfide. When the alpha particle hits it, it gives off a small scintillation, a flash of light, and they counted these in dark conditions. This is a tedious and boring experiment to do. Today, it's relatively straightforward to do. And what he found was something quite remarkable. He found that, sure enough, some of the alpha particles went through. So here's our foil. But some were deflected through small angles. Well, of course, that's what the Thomson plum pudding model would have you believe. But surprisingly, some were deflected through larger angles. In fact, some were deflected through very large angles. And even more surprisingly, some were deflected through an angle of 180 degrees. In other words, they were back reflected. And this is referred to as Rutherford backscattering. Now, this is surprising because there's no way a classical model of a uniform charge distribution would give rise to such large deflections. He was so surprised that he likened the result as if you fired an artillery shell at a piece of tissue paper and it came back and hit you. So what he was forced to conjecture was that, in fact, rather than the charge being uniformly distributed, he conjectured that there was a compact, dense region which contained all the positive charge and most of the mass. And we would call this today the nucleus. If the positive charge is localized in a small nuclear region, then the corresponding electric field will be enormous, which will give rise to these large deflection angles. The number of charged particles in the nucleus is the atomic number Z times the magnitude of the charge on the proton, which is the same as the magnitude of the charge on the electron. We're looking at the magnitude here. And for gold, Z was a large value, namely 79. And so what this means is that the corresponding electric field would be given by, the magnitude of this electric field would be given by 1 on 4 pi epsilon naught, the SI unit, times the charge of the alpha particle divided by r squared. And the charge of the alpha particle, of course, is, the charge of the nucleus, not the charge of the alpha particle, the charge of the nucleus would be Z times E. So we then have an alpha particle interacting with this large compact nucleus. R is small, this is large, so this electric field is large. This gives rise to large deflections, including, if you make a direct hit on the nucleus, backscattering. If you're further away, the deflection will be smaller. Now, what he did was he applied the laws of classical dynamics and classical electromagnetism to predict the number of alpha particles that you'd expect to be scattered through some angle theta. And he found that the number of particles that you'd predict to be scattered through some angle theta, the intensity, which is strictly speaking the number of alpha particles per second per unit area, he found that this was equal to the charge of the atomic number of the element squared, E squared on 4 pi epsilon naught, all squared, times the kinetic energy of the alpha particle squared, times this factor here, 1 on sine to the 4th power of the angle, scattered angle on 2. So what is important to note is that the intensity is proportional to Z squared. And so by using gold, which has got a large value of Z, Z squared is large, and you expect the number of particles scattered through an angle theta to be large. It's also inversely proportional to the 4th power of half the scattering angle, which means that if you were to plot this, you would get the following result. If you plot the intensity as a function of angle, the prediction would be it goes something like this. When you overlay the experimental data on this, which I'll indicate schematically, it fits it extremely well. And so when you're dealing with high angles, the number of particles that get scattered through a high angle is low, but it's not zero. And when you're dealing with low angles, the number of particles that get scattered is high. And the fact that you get any scattering at all through high angles, in particular backscattering through 180 degrees, is not in keeping with the plum pudding or the Thomson model of the atom. So what Rutherford then said is, in order to explain this result, there needs to be a compact nucleus, a region of space which contains all the positive charge and most of the mass. And this is the radius of the nucleus, which is of the order of 10 to the minus 14 meters. So this is the beginnings of the Rutherford model of the atom. It's beginnings of the model of the atom. We have a compact nucleus which contains all the positive charge, Ze, and almost all the mass. I say almost all the mass because, of course, there are electrons, but those electrons are not contained in the nucleus. It was then natural to suggest that a model of the atom consisted of a nucleus which has a positive charge in which the electrons orbit this nucleus. And the force of attraction between the electron, which has got a negative charge, and the nucleus, which has a positive charge, is the force of electrostatics, the Coulomb force. And the electron maintains a circular orbit, and the circular orbit is maintained by the force of electromagnetism. If you were to turn off the force of electromagnetism between here, the electron would just fly off at a tangent. So the electron is constantly falling into the nucleus, but it maintains its circular orbit by virtue of the force of electromagnetism. This is the so-called planetary model of an atom. It's similar to the way the Earth orbits the Sun. If you turned off the force of gravity, then the Earth would fly off at a tangent to its orbit. But of course, it maintains its orbit by virtue of the gravitational force. In the same way, it's conjectured in the Rutherford model of the atom that the electron maintains a circular orbit by virtue of the force of electrostatics or electromagnetism or the Coulomb force. There's a difficulty with this, which is apparent when you think of classical electromagnetism. If I have an electron which is a charged body and it's undergoing circular motion, then its speed is unchanged, but its velocity is changing. In other words, it's accelerating. The acceleration is center-seeking. The centripetal acceleration, which originates physically from the force of electromagnetism, the centripetal acceleration, it means that the electron is in a state of constant acceleration. A charged body, according to Maxwell's equations, when it is accelerated, or indeed deaccelerated, it gives off radiation. So according to this model, if we have the electron orbiting the positive nucleus, it should constantly be giving off radiation. If it gives off radiation, it will spiral into the nucleus. And so what we have is a prediction that matter is not stable according to this Rutherford model because the electron is giving off radiation continuously, spiraling into the nucleus, and the lifetime of this is about of the order of 10 to the minus 12 seconds. So clearly matter is stable. I'm speaking to you. I'm made of atoms. The atoms have lasted a lot longer than 10 to the minus 12 seconds, unfortunately for you. And so the prediction that the Rutherford model makes is that matter is unstable. And furthermore, it predicts that as the electron spirals into the nucleus, it emits continuously radiation. So continuous radiation and an unstable atom. We see stability, and we also see that in the case of, say, a gas of atoms of hydrogen, that far from being continuous, you see discrete spectral lines and the discrete spectral lines are not in accordance with this prediction of a continuous spectrum. So it makes two predictions which are not found in nature. Let me just finish by making a few comments about this expression here, which is the expression for the intensity or the number of particles per unit time, per unit area, which is detected at an angle theta. What Rutherford did is he applied classical dynamics and classical electromagnetism to predict the number of particles that were scattered. There's no quantum mechanics in this, but in fact it's not talking about quantum mechanics. It's just coming to the realization that in order to explain the observed results, then you need to conjecture that the charge is positive and it's localized in a very small region of space. So he applied classical dynamics and classical electromagnetism to come up with this prediction, which fits the data very well. I won't obviously derive the Rutherford formula. I invite you to do a Google search to find out for yourself how that's done. But I just will make a comment about this, why this theta on 2. So we have a alpha particle, which is incident on the nucleus, and there's the vector of the incident momentum, the momentum of the incident alpha particle. The alpha particle scatters, and there's the momentum vector for the final scattering state. Now, the momentum vectors change, the directions change, but the magnitudes are unchanged. And so I can write that the magnitude of the incident momentum is the same as the magnitude of the final momentum. Clearly, the momentum vectors have changed direction because they've interacted with the positive nucleus. But the magnitudes are unchanged. And so what this means is this is referred to as an elastic collision. The kinetic energy, which depends on the square of the momentum, is unchanged. So in an elastic collision, the kinetic energy is unchanged. So let me just call this the value P. Now what I can do is I can do a vector diagram which illustrates the process of collision. So here's the same vector Pi as before. There's Pf as before. But what I'd like to do is I'd like to calculate the change in momentum. So the change in momentum, I'll write it as the initial momentum vector minus the final momentum vector. So that's the change in momentum. Indeed, the change in momentum over a short interval of time during the collision process gives rise to an impulse from which Rutherford was able to derive this formula. And so what I need to do is calculate the change in momentum. So there's Pf, and there's minus Pf. And so here is delta P, which is Pi minus Pf. Now, you can see immediately that that angle there is the same as that angle there. You can also see that if I call the magnitude of this P and the magnitude of this P, and I bisect this angle, then this distance here is none other than P sine of this angle. But this angle in here is theta on 2. And this angle here is theta on 2. So theta on 2 plus theta on 2 gives me the angle theta, which is, of course, the scattering angle. So this I can write as P sine theta on 2. And likewise, this here is P sine theta on 2. So the actual magnitude of delta P, the change in the momentum, is just 2P sine theta on 2. That's the origin of the theta on 2 in this formula. The origin of the fourth power is a little bit more involved to derive. I invite you to do so. But in essence, one can apply classical mechanics and classical electromagnetism to get a result. So that's all I'd like to say. I'd invite you to review this material, in particular look at the relevant sections from Knight. And if you want to explore this in more detail, please feel free to ask me during the workshops.